If you have heard that you cannot do any experiment to measure your velocity in space, well, that is not correct. There are ways that you can use to measure your space velocity. They were pioneered by Mr. Albert Michelson. In this video, we'll show how interferometers that are being used every day tell us how to measure our space velocity. Following the Michelson-Morley experiment's failure to measure Earth's motion in space around the Sun, and with the development of Einstein's relativity, it was assumed that all motion is relative, and it is not possible to measure motion through space. In this video, we are going to put this belief to rest. In addition to Michelson interferometers, there is another type of interferometer that can be used to measure motion. This is the Sagnac interferometer. This type of interferometer is widely used in the commercial world, mostly for measuring angular rotation in optical gyroscopes. We are going to see how this interferometer actually measures displacement velocity and how this translates into angular measurements. Let's first have a good understanding of how Sagnac interferometers work. Let's assume that we have a beam of light traveling in a circular disk, as the figure shown here. Half the beam goes clockwise, and the other half counterclockwise from a starting point S. If the disk of radius r is rotating with an angular velocity omega, the optical path difference is given by the following calculations. For the beam traveling clockwise, the distance traveled is given by this formula. The length of the circumference, 2 pi r, plus the tangential velocity, in this case r times omega, multiplied by the time clockwise. This is also equal to the speed of light multiplied by the time clockwise. For the beam traveling counterclockwise, the distance traveled is given by a similar formula. The length of the circumference minus the tangential velocity, multiplied by the time counterclockwise. This is also equal to the speed of light multiplied by the time counterclockwise. The time difference between the two beams to get back to the same point is derived by doing some algebra. C's cancel out. We also eliminate r omega squared, since this number is very small compared with c squared. We are left with 2 pi r times 2r omega divided by c squared. We further simplified to this. This is the time difference for the two beams to come to the same place in the disk. By joining the two beams, we create an interference pattern that can tell us the angular and tangential velocities. Most uses involve measuring angular velocities in optical gyroscopes. The implementation of the disk is generally accomplished by means of a fiber optic cable. By a quirk of nature, the formula for the time difference between the two beams is the same. We'll let the viewer do the calculations. Just note that the speed of photons inside a fiber optic line has to be replaced by Fresnel formulas for the velocity of light in a moving medium. This will work for tangential velocities much smaller than the speed of light. If you do the algebra and do the same approximations as before, you should get the same formula. The important thing to note here is that there are no limits to the size of the radius. For example, a long optical fiber line that follows the orbit of a satellite can tell us how fast the satellite is moving in space around Earth. We could also send a long optical line all the way on Earth's orbital path around the Sun to measure Earth's orbital velocity. We would need to wait about an hour to be able to get a measurement, but there is no reason to think that this would not work. We don't need to worry about pesky length contraction effects either, as these have never been an issue with optical gyroscopes. But as you can see, these are not very practical ways to measure velocities in space. Some people think that Sagnac interferometers can only be used to measure angular velocities, but that is not the case. Let's assume, for instance, that we add a second loop to the disk with a larger radius. When we rotate the disk, the angular velocity will be the same for both loops, but the tangential velocities will be different. This will result in interference patterns that are different for each loop. Mr. Michelson's genius was that he realized that we don't need to go all the way around an object to be able to make a measurement. Since the tangential velocities of the two rings are different, we just need to compare a small section of the two rings to be able to determine the angular velocity. This is what he did with the Michelson-Gale-Pearson experiment, where Earth's rotational velocity was measured to an accuracy of about 2%. If we wanted, for example, To use interferometry to measure the space station's orbital speed around Earth, we would need a single optical fiber line around the station. Again, there is no reason to think that this would not work. This interferometer works every day in commercial products. But this is the hard way to do it. A small rectangle with sides of 25 centimeters and a few hundred turns of optical fiber could do the same. But this is not necessary. We already know the method works, and we already know the station's orbital speed. Interferometry does not produce a very accurate measurement either. At best, we would get 2 significant figures. Radar is a better method for measuring the station's orbital speed with high accuracy and low risk. Optical gyroscopes are built with hundreds if not thousands of turns to get an accurate measurement. They are tested by measuring Earth's rotational velocity. In effect, a repeat of the Michelson-Gale-Pearson experiment. But does this work when measuring velocities that are not going in circles? Actually, yes. A team at St. Cloud State University in Minnesota performed various experiments in 2003 using different shapes of Sagnac interferometers, and what they found was that if the length of the loop and the displacement velocity are the same, then the interference pattern is also the same. This is regardless of the angular velocity of the rollers or the area enclosed by the fiber. We can recompose the formula derived earlier to be expressed as the length of the path and the velocity of the displacement. This means that in theory, you could create any round-trip shape, elliptical, triangle, or even a 3D shape, and still measure your space velocity. You don't have to take a round trip either. You could only travel a small segment of the loop. It is important to note that you can only measure a targeted path. For example, if we place a loop on the Moon's orbit around Earth, we would measure the Moon's orbital velocity, but that would not include the Moon's velocity around the Sun. We would need a different loop for that. So what good is it to measure our velocity relative to space? Not much, really. If we have a ship traveling to Mars, the velocity relative to space is irrelevant. The only thing that matters is the velocity relative to Mars. This will tell us how long before it arrives, and to adjust the velocity so that it does not overshoot when it gets there. This is the same as an airplane flying to its destination. So if someone tells you that you cannot measure your velocity relative to space using interferometry, now you have something to talk about.